Hi, my name is Hector Garcia. I am studying energy engineering at Universidad Politécnica de Chiapas, and this is a video for my English course. Studying energy engineering has allowed me to learn about the many methods of energy generation and also has given me the chance of building some projects. The main topic of this video is a project some partners and I built the last summer. And this project was built, of course, on the middle of this pandemic, and that added a bit of difficulty to the project development. We had to improvise with the materials and also required more and more coordination and more compromise from the partners because we weren't able to work together, so we had to find a way to coordinate ourselves and divide the workload. Now I'm gonna proceed to show you the project on itself because I have taken too much time of the presentation introducing it. We decided to name this project Methane Capture System for Domestic Usage. It was built as a requirement for the subject of thermal hybrid system design, and our academic advisor was Robles Villarman Jose, PhD. Great teacher, by the way. I'm going to give you some information about the problematic we planned to attack on this project. LP gas has a great influence in life quality on urban zones. Nevertheless, on rural locations, the access to this kind of resources is complicated and normally more expensive than in cities because of the incremented cost of transportation. Agricultural waste and livestock streets have a very favorable energy potential that often goes unnoticed, and livestock streets end up being left on the pasture to become soil. Regardless its positive effects as soil by direct decomposition over pasture, livestock screeds contain methane that when it's released to the environment damages the ozone layer 84 times harder than CO2. The option offered by our work team was a methane capturing system to be utilized on domestic activities in order to shorten LP gas consumption while transforming methane onto CO2 and therefore reducing the environmental damages caused by farming activities. Methane is the main component of biogas. It is obtained by anaerobic fermentation methods. Methane combustion leftovers are CO2 and water steam. Considering that methane is 84 times more harmful to the ozone layer than CO2, it can be affirmed that it is better to burn methane than let it release to the environment. It has great properties as fuel. In fact, methane has a heat of combustion greater than gasoline. The animals with more methane on its screeds are the birds, but the most efficient producers are cows and horses. We are using cow dung in this case to fill up the biodigester. Our project deployment strategy was the following. The first stage was research. Once we had enough theoretical basis, we decided to divide the workload in two branches. One would work on the breeding report and the other one on the building of the project. Once we generated the report draft, it was revised by our academic advisor. After the approval of our academic advisor, we proceeded to develop the prototype. On the building branch, at first we modeled the methane capture process. Once we reached success, we proceeded to determine the biogas demand and the chamber size. After the evaluation of functionality of the project, we proceeded to evaluate its performance. Now I'm going to talk to you about the making process. At first, we built a chamber prototype in order to do some testing. Once we managed to capture methane on the prototype, we proceeded to determine biogas demand. For our study case, we proposed supplying energy to a stove with 4 burners. A burner has a standard biogas demand of 0.44 cubic meters per unit. For sizing, we got the following equation. Basically, it says that the volume of the digestion chamber equals 105% of the volume of the total load. So we substitute our data and obtain that we need to build a chamber with a volume of 2.4 cubic meters. We also calculated the circumferential stress strain.
This is important because if the force applied on the walls of the tank is too big, the tank could explode. The anaerobic digester is built on a plastic cylinder tank with a wall thickness of 2.2 mm, a tank diameter of 0.086 inches, and a height of 35.25 inches. To calculate the stress strain, we use the formula sigma sub index T equals P times D divided by 2 times T. T equals the tank width, D is the diameter, P is the fluid internal pressure, and sigma sub index T is the stress strain. With our data, we obtained that the energy applied to the walls was over 47 megapascals. This is way too much over the yield strength of the plastic material, so there's a problem with that. This problematic was solved and is listed on the outcomes. Now we got the outcomes. We managed to capture methane, but we noticed that a downsizing was needed. The optimal diameter is 15 inches. We managed to obtain 1.2 cubic meters of biogas out of 60 kilograms of cow dung. As a conclusion, I could say that the prototype worked really well, considering that it was built with a limited resource because of the pandemic. We decided to don't fill up the tank to its maximal capacity in order to avoid the stress strain. We are also building smaller prototypes in order to reach yield strength. Thanks for watching this video. My name is Hector Garcia Gonzalez, and I hope you have enjoyed this presentation.